All right, we're back at it. So I've been doing this book, but I wanted to go back through the exercises and try to formalize some of them just to make sure that I'm not missing anything. So I have this repo, and I tried to do some stuff yesterday, but we're gonna do it all over again because I've always liked the repetition. So we're gonna just make a 2025 12 30 Darlene. Okay. And then we are going to do this comments thing. And then that's it. And hopefully we can just and so I am using MathLib. And so the main thing that I need is this setoid. So I think if I do import math, am I going to get anything? Lib dot data dot setoid. See, that's I don't like that. How do you import this thing? No such file. Okay, so then how did they... Basic? What is the... Let's see, let's just ask the question. So we're going to start a new... What the... like, if I click on this... So this... Okay, so this is the... Yeah, so they just call it basic as the namespace. So setoid is a folder. Okay. So I think what I can do is so the first thing I want to do is remember how to use the fact that I have a setoid. So so what I'm going to do is I'm going to start off with the fact that I have some relation that's a setoid over A. So this setoid thing takes a type, and this is kind of the main departure that I've seen of Lean from just writing down math by hand, is that when you say something's a set, you don't really always say over what type. But anyways, that's there's that. Now we're gonna say that we have x, y, z of type A. So that means that they're in the type of this setoid. Then what we want to show is that we have a couple of hypotheses. And let's just make one hypothesis. So H is of type... Yeah, so H is going to be a type, I guess, of prop, right? It's going to be a term of type prop. Like, for instance, if I write R... let's put this in print. RXY... and let's just do this. We're trying to prove RXZ by, sorry, So here we go. So we're trying to prove XZ. So the point that I want to make is the type of... If I... Oops, I always do that. Okay, if I do check RXY, this is a type of type prop, right? Unknown identifier R? What? Why? It's right here. That's so weird. I feel like that's a bug or something. I don't know what the deal is there. All right, but let's make it 1 just because this is a little bit different from... Okay. So now I want to split H1. Actually, I don't know if I have to split it. I probably do. Because I think what I could do is I can do r dot trans h. Oh wait, exact. You need to do exact r dot trans h. With cases h with... That's nice. R cases. Yeah, okay, see it checked. Sometimes the messages are a little bit confusing. All right, so we... Basically what this proof is saying, this syntax is a lot, but... What this is showing is just how to use a basic fact. Okay, one thing I should say too. A setoid... Let's see if I even just click on this. A setoid is a type with a distinguished equivalence relation. Okay. And then this A... That is something else. I don't know what that's about. But anyways, so we said, okay, we have a setoid. We have 3 elements of the underlying set, or, elements of the type, I guess. And then we had a hypothesis that we know the relation between these 3 things. Now we're trying to prove transitivity. So we just use the fact that R, the setoid, has this... That's not what I'm looking for, though. I remember. I think it's just called theorem trans. So it's not in here. It's in. It's in this one. No. Where was it? Because I had it in this old one. Oh, I should be able to just click on this. What file is this in? Core? Oh. Hmm. Okay. All right. So, but now we want to start getting. Um. Now we want to show that the elements of the partition are non-empty, and the verbal proof of that is that the way that we define the partition is by the set of equivalence classes. And so for any arbitrary, elements or thing of type A is uh, equivalent to itself. Therefore, the class that it is at least has itself in it. Okay, I need to go take a shit. Okay, let's try an even simpler one. I think that this would be pretty easy too. So we're gonna have a setoid. Okay, and then we're gonna set. We would all we want to do is prove exactly what a. Let's see. How do I do this? I think because this whole thing needs to be. I think we quantify with a comma in between it, and then we want to say rxx, and then I think. Did I do it right? See, this is what. Oh wait, no, it's because I always forget the syntax. Oh. Okay, so we did it. So that's good. It's a cold one. Let's see how long I last out here. Okay, so let's get to doing something real. So now we want to show that. I guess what I want to do is go into here. There is a classes. Is it a theorem or a definition? We need to go find. Actually, can I just do this? Let's see. Theorem classes non-empty, and let's state it. Setoid A, and what we were trying to say is that the empty set is not element. How do I do a note? Lean for Unicode. I don't know. There should be a big table. What? What the hell is this? Or I guess that's not what I want. I want the like. Let's just look up lean for symbols. Let's see if I can type with. I'm going to type really slowly, but I got some gloves here. See if I can make this prolong the time I can spend outside. Okay. Oh, yeah, I can't. I have to use this thing. Okay. Show Unicode input abbreviations. Show Unicode input abbreviations. All right. That's real helpful. This list is so long. What about not an element? Oh, it's got to be right here. There's not equal. There we go. In negative. What? How are you even supposed to do that? If I do this, it eagerly changes it. What if I do that? Oh, there we go. I was just typing it wrong. R dot classes. So, okay, we can go back to this thing. I keep getting this, and I don't know what the deal is with that. So I want to rewrite the definition of R dot classes because we need to. Um, I really got to get voice working. Can I just change? Let's see. Let's look up the tactics. You do simp setoid class. Okay, so now. Okay, so now we're trying to say for all x not and then there's also I think we can now. What does just plain intro H mean there? If I just did. What does this mean? Yeah, it gets so into the weeds because like now what we're saying is um, we assume that this is true, but then we can use that to imply that x is not related to x or not equal to x. Okay, so then this are cases. Oh, see, this syntax is crazy. Are cases, and then okay, wait. Let's look up the syntax for are cases. Are cases is a tactic that will perform cases recursively according to a pattern. Think about the ways we can go here. Okay, I just want to do it the way that I want to do it. And we're going to just, because, I mean, all of these things are the same. So, they should actually have, like, a little AI built in here. That'd be nice. That, like, already has the goal state. Because I remember there was a tactic. Okay, so now okay. Oh, interesting. So now I can just do intro X. Oh, yeah. This is going to be painful to watch. Okay, so now what we want to show is basically take X1 to be X. Okay. Okay, assume the equality, then prove x. Okay, so well, let's intro h. What does that do? Let's actually do intros x h. Okay, so what did that do? What does intros do? Wait, let's do this so we can get the doc string for this. Introduces one or more hypotheses, optionally naming them or better mention them. Okay, intro h. Have hx be that x is an element. Okay, so we're saying have some other hypothesis that x is an element of this set. Okay, so I'm down with that. That makes sense. Have hx of type x in um and I should just be able to say r dot refl x, right? Unknown. Oh wait, I think I have to say exact or apply. So am I good? So now we have the x as an element. So then we want to say that x is an element of the empty set now. See, this is the problem though, is like a lot of these tactics, they're the same. Simplify h by using hx. Using this? Okay, so have h what? Of type x in. Can I just write in? Probably not. Um, Wait, oh, so we want to. Don't we want to. simp hx. Okay, hold on. Simp. The simp tactic. Oop. Oh my god, this is brutal. I'm gonna have to go inside. The simp tactic uses lemmas and hypothesis to simplify. Simp simplifies the main goal using the lemma's tag. Simplifies the main goal target using the. Oh, fuck. Simp at. Simp star at star. So I think I want to simplify hx. Simplify hx. Or no, wait. I want to simplify h at hx. Right? I think I need to, I think it can't infer this for some reason. So I need to say this is a set A. I'm not sure why. So what are we at now? Oh. Wait, why did that happen? What I'm trying to say is that we have that this is equal to this. So now I just want to put this thing. Okay. I know what it's saying, but simp A. What's the difference between simp A? Oh, using. Rewrite. I want to rewrite hx using the equation. Okay, so what? Okay. Why it works. Simp sees this and uses it as a rewrite rule. Ah, I see. Okay. Turning. Oh, I can rewrite. Oh, okay. I want to see. I want to do that one. Rewrite h. Exact hx. That's simpler to me conceptually. So now what do I have to do? X. X is in the empty set. Okay, so now what do I do? Is definitionally false, so you can finish with simp A or exact. Is definitionally false. Simp A. Okay, so wait. Let's just try exact HE. So did that work? That worked. Why is this complaining? Oh, it's a linter thing. All right, cool. So we proved the first part of it. Now we want to show that they're disjoint. Theorem, classes, pairwise, disjoint. Okay, so we're going to say R setoid A. And then what we want to say is, I think we can we do, let me think about how, all right, let's just try to do one of them. So we're going to say that H1, P1 is in R dot classes. Okay, now we need a second thing, H2, that P1 is not equal to P2. And we're trying to prove that, actually, I think that there's a type, I believe that there might even be a type where we can just say pairwise disjoint set dot pairwise disjoint of R dot classes. So let's see, what did I do wrong? Are we good? I always hate this because it's like, what is going on here? We have some sort of error. Do I have to put this in like parentheses? Do I have to give it A maybe? What is the type of this? Classes. So it takes a set. We prefer the latter in order to allow dot notation on set up, even though the former unfolds nice. Okay, that seems like something I don't even care about. What? Ooh, whoa. That's kind of cool. I just don't know how to use it. Let's try to figure this out. Type expected got so this gets rewritten into just dot pair wise disjoint. I mean, that's the thing about these errors. It's like alpha of type this to what is that? An iota? I don't even know what that is. Order bot set. Like, look at the type of this thing. What is that? Oh, really? Oh. Okay, so now I want to. What did I do earlier when I simp setoid.classes? I want to do simp set dot pairwise disjoint. Ay. Okay, and now I want to do set dot pairwise and set dot disjoint. Why did that not work? I saw it in there. Why can't I rewrite it? Unknown constant. Maybe it's not in disjoint. Maybe I just write this. Okay, so this is unraveling the whole thing. So we say for all, and then I don't know what this extra notation is with this. Like, I don't know what that symbol is. But for all x of types x is in classes implies that for all y in classes implies, yeah, and see how curried it is? I have never really, I mean, I just need practice with it, but I've never loved currying so heavily because then I always get mixed up with the types. This implies that for all this implies x not equal to y implies for all x1 containing x implies x1 containing y. Okay. So if we have a subset of x, that if we have a subset that's contained in x and y, then it has to be the empty set. So so of course they have, if we go in here, pairwise, they have the proof already. Well, let's find the simple one actually. Theorem disjoint left. Whoa. What the hell? Modus ponens reverse. I don't get that one at all. But I think that that's it. Just theorem.disjoint. No, but this is... HS is an indexed partition. Oh, these I... See, that's the thing is, when you're learning this mathlib stuff, you got to realize that I is now being used as... It's not just like a random variable name. It's actually used convention as a convention to say that whenever you have this, it's like indexed. So it usually be indexed by the nats, but you know, okay. And these proofs are tough. I feel like the right thing... Okay, so let's comment this out and just apply that R the disjoint. I don't think this works exact. But it's in here. I don't know what a set is pairwise disjoint under F if the images of any distinct two elements under F are disjoint. Ugh. Okay, so okay. Oh wait, yeah, it probably has it here. Simp A setoid.isPartition dot pairwise disjoint HC. Okay, wait, let's just see if this just does it. And then we can like look at it. Oh wow, man, dude, chat is so fucking smart. That's crazy. Setoid is partition. Like, how do I want to do it? I want to do it like this. Take I would do intros. Wait, actually, don't I have this? Oh, yeah. Okay, so I would do kind of what I was doing earlier about the goal. This is definitely the cleanest statement of the goal. But what I want to do is say that that's equivalent to saying, let's take two arbitrary elements of R, or of the classes, assume that they're non-equal, and basically unfold the definition of pairwise disjoint. That's kind of... MATLAB proves... Okay, wait, so let's try that. Okay, so now we know that R.classes is pairwise, or is a partition. And then somewhere in here is a proof that partitions are pairwise disjoint. And I think that that is going to be... I mean, it looks like it's this. Distinct elements of a set of sets partitioning alpha are disjoint. For all A, exists a unique B and C, A and B. I don't understand that. Setoid is partition. Can we look at is partition, maybe? There we go. A collection C type set A of sets is a partition of alpha into pairwise disjoint sets if the empty set is not an element of C and oh yeah, okay, all right, I get it now. But I don't really get this though. So I get that empty set is not an element of C. That's fine. And then we're saying for all A, there exists a unique B and C. Oh, such that A is in B. Okay, all right. Okay, so we have a proof of that. Okay. I'm like partially down to continue with using that. So what I want to know now is I want to say, what did I use to change? I did simp setoid dot is partition at HC. So why didn't that work? Partition. Okay, there we go. So now HC has... Can I do intros on a intros HC? Ay, ay, ay. No, I don't know what that's doing. Okay, I'll be back. So freaking cold out. So just remember exactly what we're trying to show. So kind of what we're doing is we're saying we have this setoid and we're trying to not, at the end of this, not assume that it's, or that we already have proofs of all of this stuff, that basically is partition, because from is partition we can show all the other stuff. Because we get is partition, and then where can we see setoid is partition? That's what I kind of want to know. Basically, where is this? Oh, here we go. This is it. Theorem is partition classes. So all we assume is that we have some relation R, and where you show that is partition R dot classes. And then we have this empty non-mem classes and classes equivalent classes. And where is this? Where does this live? So first let's go to this one. Set that non-mem empty. Whoa, what, dude? This is the thing about reading MathLib. Look at how much syntax is in here. There's this like this thing, and then there's this thing. Like, I actually don't like how MathLib is written because it's like, why are y'all doing all of this? Haskell like pipe operator. The empty set is not an equivalence class. Okay, well, however it may be, we actually already showed empty non-mem classes. Okay, so let's go back. What, alt arrow is not working? What the hell? Why didn't alt arrow work? What? Alright, anyways, classes, equiv classes. Okay, so here's one thing, is that in MathLib, they use a sort of different definition. I mean, it's the same, but the definition they use is different. They say basically, instead of and actually MathLibs is better than this definition. Non-empty, disjoint, and their union is S. So it's easier to show basically that for any given S, there's a unique set of P that has S, or that element of S, because that implies disjoint, since it only lives in one family. And then it also covers, because you said that for all, for any element of S. So I'm actually fine to maybe go the other way and basically do it how they did it. Is like, first we're just going to show... Oh, where was it? We're going to show that... Oh, here. This is what we were going to show now. So, and then we're going to call it a day on this one. So instead of doing this all separately, I'm just going to show... Yeah, because... Okay, so we're going to now show theorem... What would they call a property like that? I actually I wanna do this one too. I actually want to do 1.4 too, because how do you do this in lean? You know, this is like an example problem, but how do you exhaustively show that you've you know computed all the partitions? Is pre-partition? I'm down with that. Okay, so now what we want to show is that if we have a setoid, that that the classes okay, so let's see if I remember the so what we want to do is we want to say for for all x of type A exists unique. Do I just do this? Unique B in r dot classes such that A is in B. I think that that's well formed. Let's put a sorry here. I don't know if that is going to affect anything. Oh yeah, theorem. Oh wait, not A, X. Exists a unique B such that B is in R dot classes and X is in B. Okay, so the way to say this verbally is pretty easy. It's like you need to come back to what R dot classes is defined as. R dot classes is defined as the set of Y such that Y is related to X. So basically you could do this by the by contradiction. You could say take well okay. Yeah, right. So these exist unique proofs we can split into two things, right? We should be able to split this in first we need to show that there exists a B that X is in B. Then we need to show that it's the only one. So let's say, can we actually, can I, can I do like a simp, setoid.classes? Okay, cool. All right, so when you don't say, you don't have to specify a hypothesis or anything. So now we have exists a unique B, there exists a Y, B is equal to X, such that RXY and X is in B. Okay, so we're getting the hang of this, actually. Or I am, you know. It's starting to make some sense. Yes, this is right. You prove it with a witness B, a proof of PB, and a proof of, for all B prime, PB prime implies that B prime equals B. Yeah, that makes sense. Okay, this is a new tactic. Refine. Y type. This proof looks disgusting. Okay, well, it's just because I don't know what the hell refine is doing. Let's experiments. Refine E behaves like exact E, except that named or unnamed holes in E that are not solved by unification with the main goal's target type are converted into new goals. Okay, so they name the cases. Refine 1 and refine 2. So here we have a fun B to... Okay. So we want to just say that this set is in the classes and X is in it. And wait, let me remember what we're saying here. Now the second refine is for all Y of type set A. Fun B to be... Okay, so this is just the prop on Y implies that Y is equal to... So why did that happen? For okay. Yeah. This is right. This is right. This makes sense. For all Y of type set A, such that, you know, Y satisfies this, that implies that Y is equal to um yeah, okay. So, okay, so for this first one, we can say the witness is just going to be the equivalence class of X by reflexivity, and therefore it's in some class. That one feels informal to me, but let's just keep copying and pasting just to get an idea of what's going on. Oops. Shift tab. What's going on here? Why is it giving me some error? God, it's so cold. I'll be right back. These refines are so confusing with this weird syntax of question mark underscore. All right, wait, can we see? Refine E behaves like exact E. I don't get that. I don't get what refine is doing. I think it's because it's jumping through exists unique too quickly. Yes. Okay, so here's the exists unique. Okay, I forget all this. Let's go back. choose the witness B with classical. Man, there's so many tactics. Classical. Did that do anything? Classical use why type. Whoa. Oh. Okay, maybe we can use refine. I don't care. Okay, so we've refined twice. And now we need to show that this is a class. And so we should be able to just say, this is the equivalence class of X. Okay, wait. Okay, yeah, let's do that. Okay, so we want to just rewrite what the definition of classes is. So simp setoid so now we've done this. Exists Y and then we want to say use X. Did I do it? Use X exact R dot reffle. X is an element of this. But was that both of them, or was that just one of them? So wait, I think I want to do this, though. Don't I want to do... What is it? C dot? So now I have one tactic, refine 1, 1. Okay, now I want to say that there exists a... Okay, wait, what's the goal before this? We're trying to show that this set of Y that's related to X is in classes. I actually don't get how this is working. Okay, so now we rewrite this to be... I don't actually get that. What's going on there? Oh. Yeah, this thing is not bound outside of this. I think this X is bound here, right? Oh, and this Y is not bound to this. Oh, that's so confusing. What happened? Wait, can I just use X? Is that it? So take X to be this. But does it show me the rewrite? Not really. This should become Z. Okay, so then yeah. Okay. I think I get it. So what's the next one? That Y is in... So here I think I should be able to say, yeah, exact r.refl x. Okay, so we now showed that there exists a B in classes such that X is in B. Now we need to show it's the only one. So we assume that there's some other one. So this is going to be the tough part of the proof for sure. But once we do this, we're done. Okay, so now I think there's two ways of doing this. One way is to show it directly, and one way is to assume that oh wait, actually I want to just see, can I do contra? I wonder if I can just say contrapositive. I think I need to do the beta application first. I need to do this lambda first. Wait, but now contrapose is not going to work. Man, MathLib is like an insane feat of humanity. It's like, it's got everything in here. Wait, so I don't want to go the contrapose route. I think I want to prove it directly. Okay, so let me just remember, what is it that we're trying to show now? We're assuming that we have some set in the classes such that X is in there. Then now we need to show that Y is in the class of X. Or that Y must be the class of X. I wish I could rewrite this thing to Z. Can we do that? Unpack HY. Okay, I just want to see what R cases HY. Okay, this gives me left and right. So now we can say width, and then we need to do lang. R angle. R angle. There we go. I say y is the equivalence class of some w. Simp setoid.classes here. All right, let's just rewrite this like this. Fuck. Oh. So where are we at now? We say that X, such that is in the classes, and X is in oh, you can use this. This is way better than Langle. I feel like it's just so easy to get lost in the weeds here. Like, okay, refine is rewriting exists unique. Let's just okay. So here's what I want to say. We show Z. So the first thing we need to do is show it's a class. Can I put something here? Wait, what does the use tactic actually do? And then here, okay. So now we've shown that there's a class, and it's basically the equivalence. So I'm going to write that the way we do this is to effectively show that the B is the equivalence class of X. Okay, now this goal implies this is much easier than doing the pairwise disjoint proof, I feel like. Okay, so let's get a handle on this thing. So what's the goal now? So if we just do this beta application manually, we're going to get I should be able to just, intro Y. So Y is just some arbitrary set. So now we've gotten rid of the for all. And then I should be able to do this beta application, right? And what does HY do? HY does the function application. So it introduces this as a hypothesis and then makes this the goal. See, there's kind of two levels. You have to like keep the math in mind, but then you also have to keep track of all of these tactics. Okay, so we have Y is a class. Can I actually split? Oh, here. Okay, our case is HY. So now we have, okay, good. So Y is a class and we have X's and Y. Now we just need to show that X is equal to the equivalence class, or Y is equal to the equivalence class of X. Does this finish it? This didn't finish it, right? What did this do? Our cases by Simpa classes using with W riffle. Holy cow. I can't do this. I can't do this. This is like too compact for me. All right, if I'm just going to do it myself, let's see, what is it that I need to do? This arcases thing makes sense to me. Okay, so conceptually, this is what's happening. If Y is a class and X is in Y, then we have... Okay. If Y is a class and X in Y, then we can show that for all z in x r zy. By sim, we also show for all in y r zzx. This shows x. This shows x subset y and y subset x. Thus, oh my gosh, I keep clicking Alt, bro. Actually, can't I just do Alt twice? All right, that's what I'll do. So wait, let's delete this terrible line of code because that's too complicated. My proofs need to be dumbed down for me. I can't go that fast. Okay, this I understand. Have HW be that there exists a W such that Y is equal to the equivalence class of W by using the definition of a setoid's class and using the fact that we know that it is a class. So this should work. Oh. I hate the white space thing, man. I mean, it's probably better than the alternative, honestly, but still kind of annoying. Okay, so now we have the HW. Then our cases, HW, W refl does two things. It picks a witness and it rewrites Y everywhere using the equality. Okay, so let's just do that. So our cases, HW with, and then I can just do backslash this, and that's W with the witness and refl, which is like a special thing or what? I don't know what that is. Oh, cool. Rewrite X in. Wait, what is it? Oh, rewrite with the rules. So this is a list of rules. HY eq at X in. Okay, good. Can I do this too? X in. I guess not. Let's see. I like that rewrite is just like a terrible doc string. And then this one defaults at the goal. Whoa, look at how long this proof is. Let's just try to read it. Actually, that's the problem, is reading these proofs without stepping through the goal states is like kind of impossible. Okay, we did this. Oh, here. So this is actually nice because it's kind of readable. The goal is this, and X in is ooh, okay, cool. I was just about to ask, how do I obtain this? There's just so many keywords. Mm. Oh, we're so close. Okay, let me try to do this myself. So okay, so what I would do is I would say that I would call this something. I'd say that this is the class of X. And then I sometimes it's nice to break up the theorem. What if I did a new theorem where I said what are kind of the things that we need? If I said that we have um, okay, so I want to do it in a separate step. So just do a sorry here. Okay, so we have a setoid. Then we have two classes. Okay, now we want to show so how do I think I would need to use R cases. R cases HZ with and then I just do this A or no, let's say in X, in Y, like that. There we go. Nice. I'm glad that I didn't have to ask, because I feel like I need to start memorizing these tactics. Okay, so we cased it out. And we want to show that X is equal to Y. So what I want to say is, take any Z prime, or let's say, take any ZX in X. Then get R ZX X. Or no, R ZX Z by transitivity of Z is related to X and ZX is related to X. Then, since Z and Y, ZX is related to Y. So, for all ZX in the equivalence class of X, ZX is in the equivalence class of Y. Thus, the equivalence class of X is contained in the equivalence class of Y. All right. I get it. I'll be right back. All right. All right. This is going to be easy. I got this. All right. So, um, so I'm going to just go like super slowly. The first thing that I want to show is oh my God. What just happened? Have H, R, X, Z be of type R. Actually, let's do type RZX by. Why is there a sorry here? Oh. Um. Okay, so what I want to say is that have. Okay, so instead, what I want to say is, yeah. So I want to say let XE be any element of X. How do I do that? Use H1 and H2 to rewrite X and Y as actual equivalence classes. Why would you do this to me? Okay, so this gives me A1 and A2, which are elements that we... Okay, all right. I kind of get it. So now what I want to do is say, I want to build the bridge. So I want to say that because Z is in... Okay, so I'm going to say have... Oh my God. Okay. I can't do this anymore. Have H, R, or let's just say H, Z, X be of type R, Z, and I'm not doing this fucking A1 thing. Um, exact in X. Okay, cool. And now I just want to do the same thing again. Have zy be of type RZA2 by exact in Y. Okay, now I want to show have HXY be of type R A1 A2 by exact R dot trans H. I don't think this will work because let's look at the error. Exact takes a term, and rewriting is a tactic that transforms. So you can't, in the same way, but you can do rewriting inside a by block. Oh, you can just do this. That's sweet. That's very cool. So now I have RA1, A2. But that's not exactly what I wanted. But I'll need it. So the goal state is this. Now I want to take an arbitrary element in X called XE. But can I do... Oh, here we go. For each side, introduce the membership hypothesis. And how do we do this rewriting again? I think it's R cases or something. Okay, now we have two goals. So we have xe is just some random element, and we're trying to imply that this is in there. So have rxe x be of type rxe a1 by actually can't I just do first I think I need a c dot, right? And then I want to do an intro hxe. Okay, now I want to say have hxe x be of type r. Wait, I think I don't have to do a have. Can't I just do an r cases? Or no. No. R cases hxe yeah, so we need to say have of type r xe a1 by now we need the a1 a2 hxy. Why didn't that work? Wait. Wait, no goals? Wait, it's so hard to read this, dude. I wish they would make this so much better. It's like, did this work or did this not? I have no idea. I guess it worked, right? Because there's no goals. But even here we had... And then we finished, so I can get rid of this? Bro, that's so dumb. Wait, what? Oh, because this is in a buy? Oh, that's so confusing. Okay. But if I exact this... But I want to manually transform the goal. Okay, so change is pretty smart. All right, nice. Nice. So what did this whole thing show? This showed that but it didn't show... Okay, so let's do the intro HYE. Wait. Oh, wait. Okay, so what did we show here? We showed that... So before the extensionality thing, we said that these two sets are equal. Now we're saying now we're changing it to an if and only if on the elements, and we take an element, and it's arbitrary. There's no other restrictions on it. Then we do this constructor thing to break out the if and only ifs. So now we're saying if xe is in the A1 equivalence class, then it's xe is also in the A2 equivalence class. And we know that because we have this hxy thing that shows that there's a bridge between them. So first we intro the hypothesis, and then we show that this element is related to A1. And then we change the goal to showing that instead of showing that xe is in A2's equivalence class, we just show that it's related to A2, and then we apply transitivity. So now we've shown that for an arbitrary xe in A1's equivalence class, it must be in A2's equivalence class. And so we didn't actually have to do anything with contains, but it's the same as contains. So now here we need to do intro hxe again, and it's the exact same proof, I think. And this is not going to be hxe, is it? Or it is? So now all we should have to do is exact r.trans and then hxex. It's going to be hxex. Then it's going to be r.sim. And I hate that the goal state just completely goes away. It's not nice. Oh, and you can't even find it unless you delete it. That's so annoying. So we're looking for the... So it's going to be hxy. Nice. And this needs to be a C dot probably. Okay, so we're done. So now we know that I'm happy about this proof. I like this proof. I like the verbose proof. The only thing that I copied in was this stuff about the R cases on H1, which gave me... Yeah, because that was pretty complicated. Okay. So I need to remember what the hell is going on here. Okay, so on paper, so now we have this proof that R set with A, and then we have X is a R dot classes, Y and R dot classes, and Z and X and Z and Y, and then we show that X is equal to Y. Now we just have to figure out how to set it up in covers unique. So let's go. Now we show that for all Y such that Y is a class and X is in Y implies that the equivalence class of X, which is B here, okay, so let's do the intros. We have a set of A, and then, okay, we can break it up, right? Okay, we broke it up. Y is a class, and X is in Y. Now we just want to rewrite. I don't even think we need to do all of this. I'm gonna delete all of this. So this, what I want to say is that this is equal to x. So I don't even think I wanted to rewrite whatever that was. Where did I do that? That must have been like way back. Yeah, I don't even think I wanted to do that because... Alright, well, I think it should be okay. Basically, I want to rewrite this. I want to rewrite z such that rzx is equal to xc, some class. And we've... Oh, so okay, so first I want to say... I want to say that that x is an element of this by reflexivity. Wait, I want to obtain... I can just say let. Have hxc. You have type x in xc by exact r dot ruffle x. Cool. So now have xc class be of type xc in r dot classes by unfold. Okay, so by simplifying xc and then Okay, so what did we do here? So in this section, cool. So now we have these two are classes and oh, six. So we're done. So we basically now we want to say rewrite xc Well, let me just try if I do, what did I call it? Non-disjoint class setoid, H2, H2, and then in, okay, I think I can just do this manually. So first off, let's just say have HZ be of type, can I just do let? What is let? Yeah, I think I can just do this. Let Z be of type X in Y and X in XC. Defined by X in and okay, so the first thing I'm gonna do is, or I think I, Z is defined by X, but I need to provide a proof of HZ. I don't think it knows what I'm, I don't think it knows what I'm, maybe it probably does. No need to reprove extensionality here. You're reusing the lemma you already proved. Okay, let me just do it how I want to do it. Because what I want to do is, I think, exact. Did we do it? There's no thing here. I really hate this thing, man. It's like, do I have goals or do I not? Okay, we have non-disjoint class R, and then X is in HY classes HXC. Oh. Oh, wait. Okay. No, wait. I just need HXC class. And what's next? Has type. Expected to have type. Right. So we need to now do. Can I just do. XIN and HXC? What? I don't think that's going to change anything, right? Yeah, it doesn't. This worked. Oh, you can. Oh, really? Let's go. Oh, yeah. Okay. Okay, so now what I want to know, I want to do our theorem is setoid is partition. So we have an R of type setoid A, and then we want to show is partition setoid.is partition R. What? Oh, I think I need to do dot classes maybe. So first I want to do rewrite setoid.classes or setoid.is partition. Okay, cool. So now I want a constructor. Is it constructor or a destruct? Oh, there we go. Nice. All right. So, classes non-empty. All right. So exact classes non-empty are. Fuck yeah, bro. I'm so good at this now. Now we want to say for all A1 of type A, there exists a B. Okay, so I should just be able to say covers unique, right? Exact covers unique are. Oh, let's go, dude. We did it. Mm, that was fun. That was really fun. I really like this. This double check marks is great. Dude, lean is so fun, man. That was actually really satisfying. It just always takes so long to get back in the flow of how this all works. I think I'm gonna make some food soon now that we finish this thing. Probably gonna put it on GitHub. I actually want to do. Let's do. So we're trying to say. So first off, intro x. So we take some arbitrary element x of type A, and we want to show that there's a B. There exists a class B that x is in. So, um, I don't like this proof because I don't really understand it. So I think what I would want to do is I would say like have xc be defined as, or I guess let xc be defined as the set of z such that r z x. Okay, then show that xc in r dot classes and use xc as witness for b. That's kind of what I want to do, because like I don't really get this whole refine thing. Ugh, refine again, bro. Do it with use. Yeah, that's what I want. Okay. Oh, sick. Okay. Use z such that rzx. That's so much better than refine, dude. Why is big refine pushing its tactics on me? K dot. Um I'm not using their crap, bro. So what first I want to do is I want to rewrite setoid.classes, right? Can I do that? Did that work? Yeah, okay. So if I use, so I want to know what use X is really doing though. Use E1 to E2, similar to exists, but unlike exists, it is equivalent to applying the tactic refine, blah, 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 with any number of placeholders rather than just one. Then trying to close goals associated to the placeholders with a configurable discharger, bro. Give me a break, man. Okay, so wait, what did we have? We have so what I think that use X is doing in here is it's going to rewrite this X so that we have, and then it's going to, because it's like a lambda calculus shadowing thing, this X is going to be rewritten into Z. So we have Z such that RX or RZX, because we're replacing that Y with this X. And then we have equals, I don't know. It's a little bit fancy, but it's way more clear than refine. Refine is like an advanced tactic for sure. Okay, now we just need to show that X is in exact X. Oh yeah. Okay, so now I want to get rid of. Actually, wait. Is this a Git repo? Okay, so let's get rid of. Let's actually just rewrite this all over again. I think all we need to do really is just replace this. No, because that gives me this function. Okay, so cool. Rebuild it using exactly exist class for existence and uniqueness. Here are the moves. So okay, what we're trying to do. Yeah, intro removes the for all and just lets X be some arbitrary element of A. You could say element of A. Element of A and type A is the same, I think. Um. Ooh, okay. Get a witness class B that contains. Okay. Yeah, I want to do an R cases thing, so let's try that. So our cases. Do I need to do this? I think I can just provide it R. So wait, our cases. What if I just did cases? Okay, that doesn't work. No. Fuck, my hands are so cold. Okay, so that gave me that B is a set of A, B is a class, and X is in B. So now we need to, I guess we need to do this refine thing. Okay. So first, how do I rewrite this to, now I think can't I just exact, wait. Oh my God. Just gotta get this over with. So non-disjoint classes means that we have two classes with a common element and we show that they're the same. So in this case, that's basically what this is that X is the element that's common to B. Or X is in, yeah, B up here. That's very confusing. And Y. I like that you can click on it. That's nice. It's actually a pretty nice program. You can click on it and see the type of it. Okay, so can I just do intro Y? Nice. And then how do I get the dsimp? Okay, wait. No, wait. Can I just do simp? But I want to take that. Oh, wait. I think I can do intro HY, right? Nice. Okay, nice. We have literally everything we need. So now we just need to exact dis non-disjoint classes eq. Oh, I hate these names. So first we need R. Then we need something is in a class. So we need HB classes. Then we need HY. And then we need the HZ, right? And that's going to be HXB, HXC. What happened? Uh... Let's go. That's it, baby. All right, that's the stream. We did one proof today and it took 3 hours.